Okay. That?
Yes.
Okay. No, but now it's
No, I think your computer problem, you shouldn't use your computer microphone because there is a microphone in the room.
okay. So this
I think leave it as it was, and if somebody complains in the chat, I will. So far, there is no.
does this go away? Or maybe.
So I
Well, it's okay.
I will ask in the chat if there is any problem.
All right. So once more, yeah. Hello everyone. I'm here to tell you how the classical world emerges out of quantum mechanical considerations, and I want to tell you about a perhaps new approach which does not rely on decoherence. And I put a question mark there because I myself, I don't have too much background in this kind of quantum to classical transition. So I'm just entering this field, and I'm very happy to get any kind of feedback from your side on that. But just to get to know a little bit my audience, please raise your hand if you have heard the word decoherence already. That's almost everyone. Okay. I will also explain a bit. Don't worry, but that's a good to know. So maybe just as a background, I have put some references down here. So most of the stuff you will find in the first reference, which was done together with Andreas Winter, Jochen Gemmer, and Josie Wang. And actually, I think this project is kind of an interesting example how you end up in something without expecting it. Because initially, I thought about a concept called local detailed balance. I will not talk about it, but it's an important concept in non-equilibrium statistical mechanics, which basically ensures that thermodynamic entropy increases monotonously in time at each time step. But in order to meaningfully speak about it, and I wanted to derive this from like quantum mechanics, from an isolated pure state system. But in order to meaningfully speak about it, I realized, okay, I first have to talk about that things are Markovian and classical. And I thought, oh, maybe this is really hard to justify if you start with an isolated system. But at the end, I think we came up with some explanation of how classicality arises there. And this is how everything took off. And now I'm quite interested about it. So there will be another publication focused only on this classicality coming up soon. And I just want to mention two earlier papers where what I will talk about today in a broader concept was already noticed for some numerical simulations, but not really on a say deeper level than some numerical evidence. Okay, so I hope that we can start from the premise that the world around us is classical and not quantum, so they're not kind of weird superpositions and measurement back action in our everyday life. And even if you zoom in to the nanoscale, so if we look at short time scales and short length scales, and even at low temperatures, many things still look quite classical. And that's, of course, a big problem for building a quantum computer. That's why we have all these troubles since many decades. So kind of classical behavior kind of still rules the world in some sense. Now, the first important step we have to take is, of course, we have to define what do I mean when I speak about classicality, okay? And there's one big disclaimer. So there are many different ways, I think, to speak about classicality. So the border between the classical and quantum world is not one-dimensional. And there are many different ways and aspects to look at them. And I only look at one of these aspects, okay? So I'm not claiming that this is a one and only way to think about it. For instance, one way to tackle that would be, for instance, look at Bell inequalities and entanglement and say, this is something quantum, not there in classical mechanics. But that's something very static, right? Where you have one system or a bipartite system and you look at one state and look whether this state has quantum features. But I have a background more in non-equilibrium statistical mechanics, as Geta also said. And I want to look at it more from a dynamical process-depending point of view. whether you can see quantum features in a time-evolving quantum process. Okay. So the overall question I ask is, experimentally, these are 3 different experiments. Doesn't really matter what they are actually, but you run them many times and you get curves and measurement statistics, and you can plot them and do histograms and whatever. And then you might ask, okay, these curves which I collect, can they actually be explained classically, in the sense that can I also simulate them with a classical process actually, or do I really need some quantum process? And that might look like a very hard question, but actually there's a clear criterion which allows you to decide whether this is true or not. Okay. And that's written down there. Please ignore the word Kolmogorov consistency condition for a moment. I come back to that later. But let me just try to explain what I tried to write down there with this kind of notation. So I'm saying these things can be explained classically if this equality is right. And now, of course, we have to understand what all this means, what I've written down there. So let me start here with that object, Pn of xn, xl, x1. So x is just something you measure on your system, right? You perform some measurement and you get certain outcomes, and I label them x. We could think just about the position of a Brownian particle, if you like, or the number of photons in the cavity, or whatever. And now the subscript refers to a certain time. So actually, I ask, what is the probability that I measure x1 at time t1, and then x2 at time t2, xl at tl, and xn at tn? Okay. So I do n repeated measurements. I construct this giant histogram, and I just extract the probabilities from it, right? And the fact that I do n measurements is here in the notation again of the subscript. There are n measurements. Okay.
Is this a multiplication, this Pn, with this bracket, or is it a function? No.
This is the probability of measuring that. This is kind of a big joint probability distribution. And now I do one thing. I take this big joint probability distribution and I marginalize over some measurement result in the middle. Okay. So you ask, okay, I've measured n times, and now basically I average one time slice out. Okay. And then you ask whether this is equal to that object on the right. What is this object on the right? Well, there are 2 differences in the notation where I try to make clear what it is. So this is basically the same probability as over here. So you still ask, okay, I want to measure xn at time tn, and xn minus 1 at tn minus 1, and so on and so forth. With one difference, you don't measure at time tl. Okay. And this is indicated by this kind of slash notation, also by saying that this is the subscript n minus 1. So I'm only doing n minus 1 measurements at n minus 1 time. Okay. So you wonder whether at some time measuring something and then averaging over it is the same as not measuring at that time. Okay. And now in general, we know that this does not need to be the case and does not need to be the same, right? Because if you measure a quantum system, in general, you disturb it, even if you average out, your final state might be different than the initial state, simply because you delete coherences in your state by measuring, right? So in general, it does not need to be the case that the right-hand side where you don't measure, you don't look at your quantum system, is the same as measuring and averaging, okay? Is that clear that in general this is not the same?
No.
Okay, then maybe before I say more, let me.
I don't even understand really. So what is this average there over these probabilities? And this sum there?
So if you have a probability, just a probability of say 2 things, A and B, P of A, B.
Mm-hmm.
The marginal you get by summing out one of them, right? So P of A is the sum of all B of P, A, B, right?
Mm-hmm.
So this is just the marginal. I'm just summing over one probability. Okay. Actually, okay, I will come back to this slide, but maybe let me make clear that give you a situation where this is definitely strongly violated. And this is this very famous double slit experiment, which everybody knows. Okay, so you have a particle source here and a detection screen over there, and then you have some wall with two slits, right? That's a double slit experiment. And now you want to know, okay, what's the probability that my particle ends up here on that wall? And then there are two ways to look at this, basically. You know, in this one way you say, okay, well, actually, I'm interested in looking at through which slit the particle passed, right? So I'm measuring here the position of the particle at this slit, which I call x1 here, and I measure where I detect the particle on my detection screen, right? And we all know when we do this, then the final intensity profile has these kind of two Gaussian peaks, which basically correspond to more or less particles going through this slit and being deflected, and particles going through this slit being deflected, right? So this is a intensity of particles on your screen. And then we all know that when we don't look, where does the particle go through? So we are not basically looking, where is it? Then everything remains fully coherent. The wave-like nature of the particle will be still there. And then we get this nice interference pattern, which is well known from any double slit experiment. Okay. And here, so this notation is really, I only look at x2 and I don't measure at x1. That's why it's slash I don't measure at x1. Okay. Here is, I do measure at x1 and then I just integrate this out. Okay. And we know that the final probabilities can be very different. Okay. What's the reason? Well, here, because I destroy all the quantum coherence and all the wave-like properties. Okay.
Excuse me, may I ask a question?
Sure.
How do you define the notion of measurement in this theory? Because when you work with a wave function, we are speaking about some expectation values. And what is measurement here?
Okay. So then I can show one more thing before I return to the previous slide. So this is a definition of how this multi-time probability looks like, right? So this is something to write on the So you're interested in some observable which I call x, right? And you know that this observable can be always written like that, say, where these are eigenvalues and these are projectors, right? Then in each single run of an experiment, when you measure x, you get one of those x values, and I assume there are m many different.
So
right?
lambda corresponds to some quantum mechanical operators.
No, that's an operator. That's an eigenvalue.
And there is some wave
And these are
functions that corresponds to lambda.
No, so this is just the observable and measure. I'm not talking about the wave function yet. Okay. So now, what is the probability to measure something? Well, I mean, it is simply given by Born's rule. And if you apply it many times, multiple times, you get this out, right? So the probability to get xn, xn minus 1, blah, 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 up to x1 is you start with initial state, rho 0. Then you time evolve it forward in time up to some time, say t1. Then you measure outcome x1. And that is represented by projectors pi x1, which you have to apply on both sides.
But in which space do these operators actually work?
In some Hilbert space.
Okay, which still does not form the wave functions.
I'm not sure. So rho 0 is an initial state, which you can always write as a convex combination. Well, now lambda is maybe a bad idea. Right? Each psi I lives in a Hilbert space. So that operator is a linear operator on that Hilbert space. Okay. I'm not restricting the system here. This is a general thing. I'm just standard quantum mechanics.
I think if this is measuring this X operator is measuring the position on the screen, it means basically that the corresponding eigenfunctions are delta functions, right? In X, right? In the position.
Yeah.
You still can reduce it to size, to the wave functions, to the eigenfunctions of the operators, right? So like rather.
Yeah, but I mean, so far X is completely arbitrary. I'm not restricting what X is here. This was just one example I showed, but you could measure the spin, the number of photons, whatever you want. Okay. I mean,
Yeah, sure. Okay.
so it doesn't. So from that perspective, it doesn't really matter too much what this is. Yes. Maybe this was unclear. I mean, here, of course, this would be position eigenstates. But that's just a motivating example. Okay, but that would be how you define the probability to measure, x1 to xn. It's always, projector, unitary time evolution projector, and so on and so forth from both sides. Okay, so, and then it takes a trace. And as I said, whatever the pi x the projectors are, that's just in general for any observable. Okay, so let me come back here and just make a few remarks, which hopefully convince you that this is one good definition of classicality. As I said from the beginning, it's not the only one. You can ask different questions. So I think there are 3 to 4 points I want to make. Let's see how many questions we get. Maybe I only make one. No. So this definition down there, or this property, that's actually the defining property of a classical stochastic process. If you take out a textbook and look up what a classical stochastic process is, then it tells you, well, this is some joint probability on n measurements. And to get basically one level lower in a hierarchy to n-1 measurements, you can simply take the n time probability distribution and marginalize over it. Okay. And that's a little bit forgotten, actually, because people who work with classical stochastic processes typically are from the classical community. And for them, this property is so obvious that they don't even think about it, right? But as we have just seen, this is clearly what marks the difference between quantum and classical behavior in the double slit experiment. And if you look at the mathematical literature, this is known as the Kolmogorov consistency condition, okay? And that's a very important, like maybe the only fundamental axiom in stochastic processes, apart from the fact that these should be well-defined probabilities, which add up to 1 and are positive. That's one thing. So basically, what I ask is, and I think that's a very nice way to think about it, you get these curves from your experiment, and I imagine this experiment is a black box, and this could be a super fancy quantum device, might have cost millions of euros, some superconducting thing, whatever. But at the end, you just measure, you get click, 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 click here and there, and you just wonder, well, could I actually simulate this black box with a classical stochastic process or not? And if this holds, then the answer is yes. If it breaks down, the answer is no. And there must be some quantum coherence which affects the system. Okay, a comment maybe more for the experts. There's something known as Leggett-Gark inequalities in quantum mechanics. They are like Bell inequalities, but in time instead of in space. And it's known that when this property holds, so if this is true, then also all Leggett-Gark inequalities hold true and you cannot violate them, okay? So if you like to think about non-classicality in terms of these Leggett-Gark inequalities, that's included there. And another, maybe even more expert comment is that there's an interpretation of quantum mechanics known as a consistent histories or decoherent histories interpretation. I think it's more what people in quantum cosmology look at, but it doesn't matter. Then they define a definition of consistency, which is actually also exactly the same as that one. Okay. If it doesn't mean anything to you, that's fine. And yeah, I think that's all I want to say. So is it more or less clear the idea I have behind?
Violation always means quantum, or there are other ways to
Okay. I wanted to make this comment, but I thought to save time, I don't make it, but very good. No, so also classically you can violate this. Namely, whenever you have an experimentalist who's really actively intervening in the process. For instance, suppose you do feedback control or some kind of conditioning, right? Or anything where you change a process, like in the clinical trial where you say, okay, these patients, they get drugs and those get placebos or whatever. Then you will also violate this because clearly say if XL is a time where you measure the state of the patient of your patient, whether it's, you know, healthy or not, and depending on what it is, you might give drugs or not, you will change the process. And it clearly matters whether you have measured or not, right? But if you have only a passively observed process, like you start with standard classical mechanics, and you define probabilities like that, so in here there's no feedback control, no conditioning, no whatsoever, then classically this would be always satisfied from this. If you like, you know, projectors become characteristic functions on your phase space, unitary time evolution becomes Hamiltonian evolution, all that. So in that sense, in a classical mechanics context, this is satisfied. But classically, you can violate it, of course, whenever you really disturb your process. Okay. So now
In a sense, inserting projector, it's also you break your evolution, right? So it's something you put from outside. Yeah, so it's
yeah, sure. So these are from the outside, basically what the experimentalist is doing, puts projectors and gets outcomes. Yeah. Okay. So this is just a very short slide of how the emergence of classicality is typically explained in quantum mechanics. And there's one big candidate known as decoherence, which I will introduce on the next slide a bit more. But there are other candidates, and actually I'm not, as I said, an expert on that. But some say that classicality emerges actually due to gravity, where they say, well, decoherence is not fully satisfactory in standard non-relativistic quantum mechanics, but in the potential theory of quantum gravity, it's actually the gravitational field which causes decoherence in classical behavior. Sounds very interesting, but I will not talk about it. So we'll just do standard non-relativistic quantum mechanics. Then there are these collapse theories, which actually propose to directly modify Schrodinger's equation and to add some non-unitary evolution into that. And I think it's also quite interesting, but this is not what, say, the conventional quantum physicists believe so far. So I will not talk about collapse theories. And then probably, you know, at some point you have all heard about all kinds of semi-classical limits you can take. So often you compute something and then you say, oh, I take h bar to 0, or I take temperature or angular momentum or mass to infinity, and then I kind of recover classical mechanics. And I think this is, of course, a nice cross-check, but it's not fully satisfactory because, first of all, what does it mean to take this limit? Then second, we know that also qubits in a quantum computer decohere, and certainly temperature is not infinite there, or mass or so. And also the definition I put forward just 2 slides ago, I think is typically not investigated within this kind of approach. And there might be other ways to explain how classicality emerges. If you have any ideas, let me know, and I will complete the list, but this is just a short overview. And the main explanation is decoherence. Okay. So what is decoherence? Well, first of all, it's a well-known approach. There are too many reference and review articles and books. So I'm not citing anyone. So the basic idea of decoherence is to say, well, actually every system S I'm interested in is in practice always some open system, which means it's coupled to some bars B. Okay. And now, if you study open quantum system theory, where you look at how does a system involve in contact with the bars B, then this quite robustly predicts that your system density matrix loses phase coherence, so it decoheres. And this is written down there in the equation. So you might have some initial state expressed in some basis, where the rho km might have off-diagonal elements, okay? But then very quickly, the state after a shorter time t is actually diagonal in some basis, psi k, and you only have probabilities, and all the off-diagonal elements are gone. Okay. And this is what decoherence simply means. The loss of off-diagonal elements in some basis. Good questions, of course, what is a basis? This is not immediately obvious, but there's a special name for that, and it's called the pointer basis. Just maybe you have seen that. Okay. And now decoherence says, well, look, all these coherences, they are, responsible for wave-like properties and all that. So if you lose coherence in some basis, this implies that you also get classical dynamics in that basis. So that's some explanation. And I put a question mark there because on the next slide, I want to challenge this a little bit. Okay. But that's the basic idea behind decoherence. All right. So maybe before I challenge the decoherence approach a bit, I should also say that I'm not against decoherence, right? I think it's a beautiful theory. It's for sure true. If you look at a qubit in a quantum computer, this is a big problem. And there are many experiments showing that decoherence is happening. I'm just saying, okay, is this the best or the ultimate or the final or the only explanation for classicality? And I think there's much more room available to actually look at things from a different perspective. And on the next slide, I will just highlight a few shortcomings of this decoherence approach. Mostly, I must say, from a technical point of view. There's also some criticism, like from a more fundamental point of view, but I will not go into that. So I hope it doesn't become too technical. Let's see. So the first thing one has to note, and yeah, that's the most technical thing. So if you locally lose coherence, which means your system density matrix becomes diagonal, and you measure an observable x, and that observable x now only acts on the system and commutes with your density operator, this still does not imply this kind of Kolmogorov consistency condition, which I had as a beginning definition of classicality. That is only true if you make one more assumption, and that assumption is Markovianity. Okay. Now, here's the reason for that, but I'm not sure how far you're interested in knowing that. I can also just skip it, and you believe me that only with Markovianity you get this consistency condition.
Markovianity of what?
Of the system dynamics.
System path dynamics.
Yeah. So we're in the system path paradigm, and the system decoheres. And if the system is also Markovian, you will find this Kolmogorov consistency condition satisfied. In a nutshell, let me just say, maybe this is good. So we're looking at an observable which only acts on the system. And I said, if you have a decoherent state in that basis, then obviously the system state does not change whether you measure it and average or not, because all the diagonal off-diagonal elements are anyway zero, so there's no change anymore. But what is actually more relevant is whether the global system bar state remains the same when you measure an average. And this implies that, but this does not imply that. And for this reason, even if you have locally decoherent state, if you measure it and average, you might not change the local state, but you can still change the global state because there's entanglement with the bars. And if you assume Markovianity, then actually in a more technical sense, in a strict mathematical sense, say, you will get this consistency condition. And maybe if you have more questions, I'm happy to go through this in every detail later on, but maybe this is not the most important thing. Another point of criticism about decoherence is that you only look at the system density matrix. And that's, of course, a one-time object. So really, if you want to compute correlation functions, so what happens here and then here and then here at these 3 points in time, if you want to make some claim about that, then this one-time object is not enough, unless, again, you add the addition of Markovianity and say like, oh, all correlation functions are given in terms of 2-point correlation functions, which I can compute with a master equation. So the first two things just say decoherence plus Markovianity. This gives you classicality, but otherwise it's actually more subtle. Another question is, what is actually the pointer basis? So, your open system density matrix decoheres in some bases, but for sufficiently complex system and bar, it's not at all easy to predict what is actually the pointer basis. So in which basis do you expect classical behavior? I think there are only limiting results known. Then there's a point of circularity. In which sense? So when you take out a book of open quantum system theory, then the typical initial state from which they start and derive everything is, I have a system state decoupled from a bars, and this bars is in a canonical ensemble or Gibbs state. Now, if the bars is really big and far enough away from its ground state, then the Gibbs ensemble is a very classical state. In a sense, it's a highly mixed state. It's far away from being pure. So then what decoherence tells you is like, oh, if I have this giant mixed super classical state in the bars, then my system will also become classical, which is a bit circular because you put in a lot of classicality, right? So it would be much more impressive if you could show, oh, even if the bars is prepared in a pure state, things will look classical, and we will actually see that in the talk. And I think the final, well, this is just, if you look at decoherence, you always have the system bars tensor product structure, but you might be interested in observables which are not defined on a local subspace, but maybe some global observable, which acts on the full system bar space or something else. Okay. So let me just summarize. So I just introduced to you a notion of classicality, which is really comes from the idea to ask, does a classical stochastic process suffice to simulate your measurement results? And I showed you a very nice idea, which is decoherence. And I'm not against decoherence. I'm just saying it might not be the only and the perfect answer to that question. And now I will talk about what I call a new approach. Maybe it's already known, let me know, but I was not able to find anything about this in the literature. And that setting is quite different because we really say we want to start from an isolated system. This system might be the system and the bars, but it does not need to be. It's something isolated. But it's a many particle system, so there's a huge Hilbert space dimension, and it should be non-integrable. And then the initial state is a pure state, psi 0, and it can be almost everything. I'm just saying, well, it should have a well-defined energy E, okay? Because energy is strictly conserved in an isolated system, so if you have kind of a Schrödinger cat state, which is a superposition of two very different temperatures, you should, apply your analyzers to each energy sector separately, okay? So basically, the energy spread of the wave function is not very large. And then there's some observable x in which we are interested, and we want to find out whether dynamics is classical with respect to x. And maybe that's a good point to add. I forgot this. So the same quantum system can behave quantum with respect to an observable y and classical with respect to an observable x, okay? So whether you observe classicality or not definitely depends on what property you're looking at, okay? Now,
sorry, what you said about the energy of the initial state, does it? So that doesn't mean that it is an eigenstate of the Hamiltonian? Not necessarily.
no, it can be still like a superposition of many eigenstates, but the variance in energy should not be too large.
Okay.
Right? Yeah. So, like for standard statistical ensemble, right? You also have that the mean divided by the standard deviation. No, the reverse thing is 1 over square root n. So it does not, you don't have a huge variance in energy in ensemble. Okay. Now, so I cannot show that classicality arises for every observable x, because that would be simply not true. I need some assumptions, and the two assumptions I need is that the observable x is coarse and should be slow. So what does coarseness mean? And I think this is really not an assumption. So it means that the number of different measurement results m, which I can distinguish, that should be much smaller than the Hilbert space dimension d. And for many body systems, the Hilbert space dimension d scales exponentially with a particle number, right? And experimentally, you can never resolve that many digits in your whatever microscope. So this will be, this is not really a real assumption. Okay. What is a more subtle assumption is that you say things are slow, and I have two ways to explain this. One way is about timescales. So let's say tau of x is a typical evolution timescale of your expectation value of x, right? So just assume you plot x of t, and then there's a characteristic time where this expectation value starts to change, and this is my tau of x. And you say this should be much larger than this. What is that? Well, this is h bar, this I guess. What is delta E? Delta E is exactly the spread of the initial wave function, the variance in energy, if you like, or the standard deviation. Okay. Now, what is this time scale? Well, this time scale is actually a microscopic evolution time scale. So this is roughly the time scale you need to map some vector in your Hilbert space to an orthogonal vector. And this follows rigorously from something known as the quantum speed limit, but doesn't really matter. And just say, this is the time scale for microscopic processes in your system. And because you have a coarse observable, I demand that the time scale on which this observable changes is much slower than the very fast microscopic time scale. If you don't like this explanation, here's number two. Assume that you write down X as a matrix in an ordered energy eigenbasis, right? So you just take its matrix elements and you order the energy. Then a slow observable means that X is a narrowly banded observable. So off-diagonal elements are strongly suppressed.
So the energy should be defined with respect to certain Hamiltonian, right? So
Yes.
we assume that there is a Hamiltonian of a system.
Yes.
And if this Hamiltonian is changing in time or it's stationary.
Yeah, this is a good point. So the Hamiltonian is time independent. We have a
Okay.
Hamiltonian, it should be a many particle system, should be non-integrable, but time dependent, time independent.
And then this means that the second equality it cannot be satisfied for an eigenstate, right? Because if your delta E goes to 0, then
Yes, but an eigenstate is anyway no longer changing in time, so you would say there's anyway no dynamics. So yeah, I mean, basically,
which means that you're looking for evolution of a wave packet. So yeah.
yeah. So I mean, basically, the way to think about it is, you have your spectrum of your many-body system, all the eigenenergies, right? Starting, say, from a ground state energy, which we can put to 0. And I say I pick some energy interval here, which has some fixed width delta E. And I only want to make a claim about all kinds of wave functions which are in this energy interval, assuming that delta E is not very large. But it's still large enough such that the number of states here is really very big because the many-body system. Okay.
And you take a random state out of this, basically, not a special one like a particular eigenstate.
Yes, so this is something I will not talk about too much. Okay, but maybe I come back to this later. Let's see. But the point is, we can choose non-equilibrium states, but it's not good to choose an arbitrarily fine-tuned state. Then you can violate things, which maybe is not too surprising. Okay, this is a setup and the central assumption. Now comes a result. Again, it's a little bit technical. So remember, it's this Kolmogorov consistency condition for n times. If you take an arbitrary n, you just get lost. It's really hard to work with it. There might be some very nice mathematical tools to address it, but all that I was able to look at is a 2-time thing. Or if you like, it's 3-time thing. You have initial state, propagation, measurement, propagation, measurement. So that's the probability to have these two measurement results. And then I look at this one where you where you don't measure at x1, which simply means that you have to remove these projectors so they don't appear here anymore. Okay. And then I subtract these two things and I sum over x1. And this is, say, my quantum term, right? And this is in between plus minus 1. Okay. And this basically signifies how strong quantum effects are. And now what we kind of derived is the following, and I will explain it a bit what it means, but I will not go into technical details. It says that something which is called the eigenstate thermalization hypothesis implies that Q goes like 1 over d to the power of alpha, and d is the Hilbert space dimension of your many-body system. Recall that this is exponentially large in the particle number. And alpha is some exponent which is not universal, unfortunately, but depends also on the initial state. And this is a very weird notation, but I want to say that alpha is of the order of 1 over 4, 1 over 2, or something like that. So it's not super small, but smaller than 1, okay? So this means if you have, if d goes, say, 10 to the n with n the particle number, and you have 100 particles or whatever, then this is really, really small, that term, okay? Here are two things I might have to clarify. First, eigenstate thermalization hypothesis, or for short, ETH. Who has heard about this? One. Okay.
What's the name?
Eigenstate thermalization hypothesis. Okay, so then you have missed something big, or maybe not. I don't know. No. Okay, this is so far all the audience where I get to talk than you about it. So that's the hypothesis for, I mean, I've written it down here. It goes back like 30 years ago to some work. You take some observable, here is the projector pi x, and you look at its matrix elements in the energy eigenbases. So EK and EL are the eigenvectors of your Hamiltonian, right? And this ETH says that for like all kinds of relevant observables you might be interested in an experiment, these matrix elements have a universal form, okay? There's a diagonal term which looks like this, and actually if you think about what this is the expectation value of this operator in the microcanonical ensemble, okay? And then there are off-diagonal terms which are suppressed with the Hilbert space dimension, and we have these two functions, and this is kind of a smooth function, and these RKL, these are pseudo-random numbers of variance 1 and 0 mean.
What is omega there?
Yeah, actually, omega is the energy difference, EK minus EL. Sorry. Yes. And this looks a bit like magic. So this is an ETH says you take any quantum system, you take almost every observable, you look at matrix elements in that, and they look like this.
But this is an assumption, or
It is a hypothesis. And I think there's only a rigorous derivation of that if you either use random matrix theory from the start, or if you go to the semi-classical limit of a quantum system which has a classical chaotic Hamiltonian counterpart. And then this actually goes back to work of Berry and others. But the amount of numerical evidence for that is overwhelmingly large. And basically exceptions are integrable systems, but almost all non-integrable systems you meet will have that form, okay? And that's why people are really excited about it. And there are many subtleties, which I will not tell you, because this will be an entire lecture series of this. But this is believed now by many to be the explanation how thermalization arises in an isolated many-body system. You can say this is kind of an explicit way to look at what quantum chaos means what chaos means in quantum mechanics. Okay. Yeah. Okay, I'm sorry, I was not prepared that this would be so new. So I hope I could kind of at least explain what this roughly means. Okay, and then there's implies in these quotation marks, because you might imagine that doing calculations with that is, I mean, these are kind of estimates and derivations you do, but they would not qualify as a mathematical rigorous theorem. Okay, so that's why I said, okay, maybe be a bit more careful with the language and don't say that this is a theorem, but we estimate that. Okay. And I have a numerical example for you which proves this to be true. So what we have is a spin chain. These are the Pauli matrices basically. And you have interactions between nearest neighbors and also between second nearest neighbors. That one is known to satisfy the ETH if you're not in the integrable limit where these delta terms are zero. And we look at an observable, which is defined here, and which is like a spin density wave, you could say. So you add up the local spin operators, 5 more minutes. Ah, great. And then you modulate with a cosine. And now there's a dependence on Q. Depending on how you choose Q, you can actually change between a short wavelength or long wavelength observable, which means a fast or slow observable at the end. And what we see if Q is small, which means that it's a slow observable, we get these kind of plots. So these are the different sizes of the system. This is this quantum term, which I just introduced before. And we look at its time evolution, where time is normalized to thermalization time of that system. And you see that it stays very small. And here's some kind of scaling law over the system dimension. And here's the exponent alpha, which I had on the previous slide, would be roughly 0.3. Okay. And this is for the fast observable, so where Q is basically large. And you see, for later times, it also becomes relatively small. And if you average over that, you get also a scaling behavior, which goes down. But at least for short times, things look very non-classical, very quantum. So this quantum term is 1/4 here initially. And I told you it's between plus minus 1. So this is kind of a pretty strong violation. So this is numerical evidence. Now I have 2 more slides before I conclude. So just maybe to mention, I worked a bit further on it. And this time I really used the random matrix theory approach. So I think random matrix theory you have heard of, right? The idea is just things are too complex, so you just model it randomly, the Hamiltonian. And the idea is you have an Hamiltonian H0, some baseline Hamiltonian, and then you add a weak random perturbation to it. And that's your isolated system, okay? And I demand that my observable X commutes with H0, which for small epsilon implies that X is evolving on a slow time scale, right? And then again, it's not a true theorem because even if you work with random matrix theories, things you have to take ensemble averages over random matrices and you don't fully know the statistics. It's really hard to control them, but often works well in practice. And then the term Q squared actually, so not Q, I show that this goes with D over D, so this to the power of 4. That's the full Hilbert space dimension, you know this already. What is D? Well, I told you that slow observables are narrowly banded in an ordered energy eigenbasis. So this small d is kind of the bandwidth of X. So basically tells you that you can set these off-diagonal elements to 0 if K minus L is larger than D, okay? And of course, if you have a slow observable, then D is much smaller. So small d is much smaller than capital D. So you have a small number on the right-hand side. And again, this is just a more general result. Now I look at a certain system where I have just 2 energy bands, B1 and B2, they have equally distant energies, and then I couple them via some random matrix, okay? This is just a fully random matrix, epsilon is small, and this is an observable where pi2 is a projector on the full second energy band, pi1 projects on the first energy band, So I just look at the energy imbalance between the two bands. That's all. This is just normalization. You can ignore it. And actually, now we come back to your question. So this is a fully random state. This is how randomly chosen, but only living in pi 1. So I say all the energies in band 1 initially, and it's a random state. And now as a function of n, so n is here your system size.
Sorry,
Yes.
Is this randomness in time?
No, so you just say it as a Hamiltonian, and this V matrix, this is just randomly chosen, but fixed in each run of the experiment.
Okay.
Right?
So
So you just take a random matrix, and this is your Hamiltonian.
So you make an ensemble of systems basically,
Right.
and then you average over this ensemble of
But the point is that the curves I show there, they're not averaged. They are for one realization of that random matrix.
Mhm.
And why does it work? Well, because there's something like typicality argument behind it, which tells you almost all random matrices you choose give rise to the same behavior. That's why random matrix theory actually works. That's the magic behind it. This is it. So what I want to show you here is just at that point, I do the first measurement, so basically I dephase the state, I delete the coherences, and then I look at the evolution of, well, P1 of t is actually the probability to be in the, I mean, it's a, I think it's this expectation value plus 1/2. Sorry for that confusion. Anyway, if you have a small system size and it's only equal to 60, you see that so the black curve is without any measurement, right? So this would correspond to, let me see, to that thing, and then this one is, this is the one without measurement. This is with a measurement average. So without measurement, you get the black curve. With measurement, you get the pink curve, and they differ a lot for a small system. But if you go to a large system, you see that they very nicely are actually the same. So it doesn't matter whether you measure an average or not, you get the same dynamics. That's exactly the claim. Now there's one final thing I want to say, and this is related to this value delta above here. So that value is the trace distance at that time between the pure state and the dephased state. So the dephased state is just a state where you measure an average, okay? And this is here with a D marked, okay? And well, what is the trace distance? Well, it's some kind of focus from the quantum information community. It's a measure to look at how different two quantum states are. And this is what they like to compute a lot because there's a lot of nice properties and actually tells you, so 1 plus the trace distance divided by 2 is the maximum success probability to distinguish two states, given that you have complete measurement power and can do whatever you like, okay? And that thing is in general bounded between 0 and 1, but you can show that for this specific case for dephasing, it's actually bounded between 0 and 1/2. So 1/2 is the maximum of this expression. And that would tell you that these two states are very different. And now you see here, this and this and this is very close to 1/2. So it's really that the dephasing or the measuring and averaging is really destroying a lot of coherence. It really changes the state completely. But in the dynamics, you cannot see it at all. And I think this is a nice thing, which really says this is completely different from decoherence, because decoherence says these off-diagonal elements don't exist. They get kind of decohered, which would mean that really this expression should be 0 because there are no off-diagonal elements. But here, really, there are a huge amount of coherence is involved, but they do not become visible in the evolution of that observable. They might become visible if you look at a different observable, but not in that one. And that was a main message. This is the conclusions. So,
Sorry, does it mean that for this observable we can write a kind of classical equation of motion for the expectation value?
exactly. So actually, this for a large n, this follows a nice exponential decay to as you would expect from a classical Markov process. Exactly. Okay, so let me wrap up very quickly. We started from a non-integrable many-body system, an initial state confined to some energy shell, okay? And the important thing is that you have a coarse and slow observable, and in particular, slowness is a bit subtle, this assumption. I didn't talk too much about it, but I just want to raise awareness of that. And these three things are sufficient to imply classicality, and we don't need decoherence, we don't need to impose Markovianity. There's no need to find a pointer basis. This was done for initially pure states, so we don't have to work with a Gibbs state and put in a lot of classicality. And there's also no system bars tensor product structure here from the beginning. You can apply it to it, but it also works for isolated systems. That's all I wanted to tell you. I hope you took something away from the talk, and I'm much looking forward to your feedback.
Thank you very much. So we had already some questions. But,
Yeah, just continue to the previous question. This is a classical equation of motion. Can you write it down without all this business, simply looking on your Hamiltonian, and you take your observable, and without this, can you derive this classical equation of motion, which you're getting by
Yes.
this machinery?
So I mean, actually, this was
Just setting h part of 0 or what?
no. This is exactly actually the content of this paper. We say we start from an isolated system in a pure state, and we look at a certain observable and we want to find out. Wait, here we go. And you want to find out whether the probability to be in state X as a function of time, does this evolve according to some classical rate equation where you have some rate matrix, let's call it R, like that. That would be a classical master equation, right? Just a probability balance equation. And we want to derive this from underlying quantum mechanics without using any ensemble averages and all that.
Is dissipative at any rate. Yeah, so this equation, the first order differential equation. So it's not
Yes.
like the non-dissipative classical dynamics, right?
No, exactly. I mean, because X describes only a gives you some information about your system, but it does not evolve in any kind of, so this thing does not need to evolve in any kind of reversible way, right? And actually, yeah, when you assume these kind of slow and coarse observables, what we argue is that you get this out. And in that sense, I think you were right. This, if you would, the exact solution of that is just exponentially damped oscillations, right?
Yeah. This is what I mean.
Yeah.
But you cannot get the non-dissipative classical dynamics out of this, yeah, because it's
what is non-dissipative? You mean like Hamiltonian mechanics?
like Hamiltonian mechanics.
No. This is not. For this we really need. Yeah, I think for this you need to do different things.
So it's a kind of emergence of classical dissipative dynamics, yeah.
Yes.
Not classicality, as we would expect from Newtonian mechanics or something.
No, exactly. So I'm not trying to go to the limit of Newtonian dynamics. Yeah.
more questions? So if you were to involve more than one observable in this description, you could still so would the classical definition of a process still apply? That
in principle, yes. You could say something like, now I measure this observable, a time later I measure another observable. We haven't looked at this. I think it's much more, well, maybe it would not be too much. The complication arises when you start thinking about, I want to measure both at the same time, right? I measure this, of course, is, but if you say, I just measure always one at one time, you could apply this, and probably you could also show some classicality if both are slow and coarse.
so if you were only in the classical regime, you this Kolmogorov consistency condition is still applicable, and you can characterize sort of multi-observable classical processes
Yeah.
in this way.
Yeah.
And then it may be harder sort of to or the system, like you said, the system might not behave classically for a given observable, it does for another. Then if you wanted to behave classically for a whole collection of observables, it is a larger demand.
Yes.
But they're depending on the choice of observables and dynamics.
Exactly.
Mhm. And then you would have this, then the system would have the space also to contain Newtonian dynamics, or then it could you could have some
Right. Yeah.
X and P rotating into each other and so on.
Yeah.
So I just wonder if, I mean, that's also that you get this very simple dynamics comes from the fact that you look at it only with one particular observable.
Yeah, that's true. So I mean, it's not so trivial to extend this to multiple observables. I think some stuff is probably doable easily, but much stuff is not known. But yeah, but I mean, as you saw from the examples, I'm not really interested in this kind of Newtonian case. Because I show the spin chain thing, you know, like, so, and I think it's not a contradiction to Newtonian, because, okay, Newtonian dynamics would be something even on top, because here I asked, can you simulate something with a stochastic process, which is still very noisy in principle, but Newtonian dynamics, you would say, okay, this gives me then also deterministic dynamics, right? And I was not interested in this additional limit.
More questions? Okay. If not, then let's
Thank you. I think it was much over time, but there were so many questions.
Yeah, no, I think it was we start with this later. Was fine, and I think it's good to address this. I had
I come back in 2 minutes.